You know, when we talk about artificial intelligence today, there's this massive unspoken assumption underlying almost every single tech headline you read.
Right. It's everywhere.
Yeah. And the assumption is basically that if an AI can talk to us perfectly, if it can, write a sonnet or summarize a dense legal brief in flawless English, it must understand the world perfectly.
Which is a huge leap to make.
Exactly. But think about that for a second. It's like assuming that someone who has memorized a highly detailed, incredibly complex map of Paris knows exactly what it feels like to actually walk its streets.
Oh, that's a great way to put it.
Right. Like, they know the names of the roads, sure. They know the exact geometric distance from the Eiffel Tower to the Louvre. They can give you turn-by-turn directions.
Yeah, the literal data.
But they don't know the feeling of the cold wind coming off the Seine in February. They don't know the smell of the bakeries opening at 5 in the morning. And they certainly don't have the physical reflexes to dynamically jump out of the way of a speeding scooter on a cobblestone street.
Yeah, because the knowledge they possess is entirely symbolic. I mean, they have the vocabulary of the city and they have the syntax of the grid. But they possess absolutely none of the physical grounding. The map, as the old saying goes, is not the territory.
The VAP is not the territory. Yet the entire Silicon Valley ecosystem right now is basically pouring hundreds of billions of dollars into making a better, more detailed map.
Hoping that eventually, if the map just gets big enough, it will magically transform into the city itself.
Exactly. But Yann LeCun, who is literally one of the godfathers of modern AI, just looked at that map, called it a dead end, walked away from his empire at Meta, and took $1 billion with him to start over from scratch.
It's honestly one of the most stunning pivots in the history of computer science.
Yeah.
I mean, LeCun won the Turing Award, which is basically the Nobel Prize of computing, for his foundational work in neural networks.
Right, so he's not just some random critic.
Exactly. He is not a sideline critic at all. He built the foundation of the house the industry is currently living in. And to understand the sheer magnitude of what he is doing now, we have an extensive stack of source materials to guide us through this deep dive.
Yeah, we've got a lot to cover for you today, so we are pulling from a highly candid, exclusive interview LeCun gave to the Financial Times.
We're also diving into some really dense technical preprints on what are called JEPA architectures, specifically unpacking things like V-JEPA 2 and the purely mathematical LeJEPA.
Plus, we have a newly published, incredibly provocative theoretical paper on superhuman adaptable intelligence, or SAI. And finally, we are parsing the breaking financial and structural news surrounding his brand new, massively funded startup, AMI Labs.
Right. It's a massive stack of info.
It really is. So our mission for you today is to go over absolutely everything Yann is doing. We are going to deconstruct his radical philosophy on how artificial intelligence actually learns.
We'll break down the math behind how his new systems perceive reality, too.
And we're going to map out exactly where this multi-billion-dollar bet is taking the future of technology. So let's unpack this from the very beginning. Why is a pioneer of modern AI suddenly abandoning the current industry darling large language models?
Well, to understand the technology, we first have to look at the fracture. The catalyst for everything we are going to discuss today is his departure from Meta.
Right. And he was there for a long time.
Over 12 years. He served as the chief AI scientist and was the founding director of FAIR, which is fundamental AI research. And FAIR was historically treated almost like a university lab operating inside a massive corporation.
It was very academic, Rip.
Very. It was driven by open-ended scientific inquiry, but the internal dynamics at Meta shifted violently in late 2024 and early 2025.
Yeah, the reports in our stack highlight a pretty dramatic change.
Exactly. We are looking at a reported 600-person layoff within Meta's legacy AI research product and infrastructure units.
Wait, 600 people in the middle of an absolute AI gold rush?
Yeah, I know.
I mean, companies are normally fighting tooth and nail, offering insane compensation packages to hire anyone who can even spell neural network. Laying off 600 AI specialists right now seems totally counterintuitive.
It is highly unusual, which points to a fundamental shift in corporate strategy rather than just, standard cost cutting. The reported goal was to radically streamline operations under a new executive, Alexandr Wang.
Okay. And he was brought in to lead what?
He was brought in to lead the newly formed Superintelligence Labs unit. And we actually have details from Wang's internal memo outlining the philosophy behind this purge.
What did he say?
Well, he stated that smaller teams require fewer conversations to make decisions. He wanted each person to be more load-bearing, meaning every individual researcher or engineer carries a massive amount of direct product responsibility.
Instead of just doing like theoretical exploration.
Exactly.
So it was a shift from let's figure out the mysteries of intelligence to let's ship a product next week.
That is the reported crux of the internal friction. You have Wang pushing for these highly streamlined, product-oriented teams that are aggressively competing for Meta's massive computing resources.
Right, all those giant clusters of NVIDIA GPUs.
Exactly. And on the other side, you had LeCun and the legacy fair researchers who wanted to pursue longer-term foundational shifts in architecture.
And just to be clear to you listening, we are reporting this completely impartially, just looking at the facts presented in our sources. We're not taking sides on corporate strategy here.
Right, we're just analyzing the fallout.
Yeah.
And LeCun expressed immense frustration with what he described as an LLM-pilled culture taking over Meta.
LLM-pilled. I honestly love that phrasing. It paints such a vivid picture of a company just totally intoxicated by the success of ChatGPT.
Yeah, just deciding that generating text is the only thing that matters anymore.
It really describes a monolithic mindset. The idea that scaling up large language models is the singular path to artificial general intelligence.
And this tension really hit a boiling point around the release of Meta's flagship model, Llama 4, in April 2025.
Oh man, the Llama 4 controversy is wild, especially coming from someone who is still deeply associated with the company at the time.
It really is.
In his interview with the Financial Times, LeCun essentially blew the whistle on Meta's own AI operation. He admitted that the published benchmarks for Llama 4 were misleading.
Yeah, he actually used the phrase that the results were fudged a little bit.
For a chief AI scientist to use the word fudged regarding a multi-million-dollar flagship release, that is unprecedented.
Completely. He revealed that the engineering team actually used different specialized models for different benchmark tests in order to game the numbers.
Wait, really? So the model taking the math test wasn't exactly the same under the hood as the model taking the coding test?
Exactly. But the results were packaged and marketed as if a single unified Llama 4 model had achieved all of it.
Wow. And that leaked almost immediately after the model's release, causing a major credibility crisis, right?
It did. But, you know, reading between the lines of the FT interview, it seems LeCun's frustration wasn't just about PR or fudged spreadsheets.
Right. The fudge numbers were just a symptom of a much deeper structural disease.
Yeah, he was pointing out that LLMs are hitting a wall, and to hide that wall, companies are starting to cheat.
Let's really dig into LeCun's philosophical critique here, because this is where the science gets fascinating. What is his fundamental issue with LLMs?
At its absolute core, LeCun's argument is that large language models are structurally incapable of achieving true human-level intelligence because of their fundamental learning objective.
Okay, break that down for me.
Think about how an LLM is trained. You feed it vast, unimaginable troves of text from the internet, and you give it one very simple mathematical objective: predict the next token in a sequence.
Right. And a token is usually a word or a piece of a word.
Exactly. So if the input is the sky is, the model adjusts its internal weights until it correctly predicts blue.
Which, to be fair, is incredibly powerful for certain things. I mean, if I need a model to summarize a 50-page PDF or write a Python script for a web scraper, predicting the next token works brilliantly.
It does. But text is a closed system. It is discrete.
That word discrete is the key, isn't it?
Yes. Text is a finite set of symbols. There are only so many words in the English dictionary. But LeCun argues that mastering the statistical relationships between these discrete symbols does not equate to a grounded understanding of the physical world.
So they are basically just brilliant mimics.
Right. They can generate a perfectly structured essay on the physics of a black hole, but they don't actually understand gravity.
They hallucinate facts. They struggle with reliable, multi-step, long-term planning.
And most importantly, they lack the basic, intuitive common sense that a human toddler possesses simply from interacting with the physical world.
I want to go back to my driving analogy from earlier to really flesh this out for you. Relying on an LLM for true intelligence is like trying to teach a teenager how to drive a car by locking them in a room with a million driving manuals.
Okay, I like where this is going.
So they read the manuals over and over for 10 years. They can recite the exact stopping distance of a Honda Civic traveling at 60 miles per hour on wet pavement.
They can quote the local traffic laws perfectly.
Exactly. But they have never actually sat behind a wheel. They have never felt the heavy resistance of a steering column when the power steering failed.
Right, they have no physical context.
They've never felt the terrifying, weightless sensation of a car hydroplaning over a puddle. If you put that teenager in a real car on a real highway, they would crash in 30 seconds.
Because the sensory input of reality cannot be fully captured in text. Your analogy aligns perfectly with a concept brought up in the sources known as Moravec's paradox.
Oh, Moravec's paradox. What is that?
So Hans Moravec, a robotics researcher, observed decades ago that what we consider high-level, sophisticated reasoning like playing grandmaster chess, solving calculus equations, or passing the bar exam actually requires very little computational power.
Really? But that seems so hard for us.
I know, but low-level sensory-motor skills like walking across a cluttered room or pouring a glass of water without spilling it require enormous, staggering amounts of computational resources.
That is so counterintuitive. We think of chess as the ultimate sign of genius, but an AI conquered chess in the 90s.
Yep. Yet if I ask an AI robot to fold my laundry, it completely freezes up.
Why is laundry so hard for an AI?
Because folding laundry requires continuous, real-time physical interaction with a highly deformable object. A shirt doesn't have a discrete number of states like a chessboard.
Oh, right. Every time you touch the fabric, it wrinkles in a completely novel, unpredictable way in three-dimensional space.
Exactly. Your brain processes that visual and tactile feedback in milliseconds, updates its physical model of the shirt, and adjusts the tension in your fingers. Reality is not tokenized. It is continuous, it is noisy, and it is infinitely high-dimensional.
And this leads to one of LeCun's most famous and, frankly, hilarious quotes from the materials. He basically looks at these massive trillion-parameter LLMs that everyone is calling super intelligent, and he says, well, it doesn't even have the reasoning capacity of a house cat.
And he is dead serious about that metric. He argues that the AI industry is entirely focused on the wrong milestone.
How so?
Everyone is panicked about reaching human-level artificial general intelligence, but LeCun points out we haven't even reached dog-level intelligence yet.
Dog level.
Yeah. Think about it. A dog understands object permanence. If you throw a ball behind a couch, the dog knows the ball still exists and will run around the couch to find it.
Right. The ball didn't just cease to exist because it's out of sight.
But an LLM doesn't understand that. It just knows the statistical probability of the word ball appearing near the word couch.
So LeCun's philosophy is that once you solve dog-level intelligence, once you have an AI that intuitively understands the physical physics of the real world, the jump from primate to human reasoning is actually relatively small in comparison.
Exactly. The physical world is the hard part.
That completely flips the script. We are terrified of these digital gods, and LeCun is sitting there saying, guys, it can't figure out how a bouncing ball works. It's dumber than a golden retriever.
It really puts things in perspective.
So if LLMs are a fundamental dead end for true physical understanding, what is the antidote? How do we build a system that actually understands the world like an animal does?
This brings us to the theoretical core of LeCun's entire new venture. It's the concept of world models and the specific mathematical architecture he has pioneered to build them, known as JEPA.
Okay, let's define the terms before we get into the math. What exactly does cognitive science mean when it uses the phrase world model?
A world model is an internal dynamic simulator of reality. Evolution has equipped humans and animals with this simulator, so we can predict the consequences of our actions before we actually execute them.
So it is the biological mechanism for goal-oriented planning. Okay, let's use a physical example to make this concrete for you. I am walking down a busy sidewalk after a rainstorm, and there is a massive muddy puddle blocking my path. I don't need to actually step into the mud to find out my shoes will get ruined. In a fraction of a millisecond, my brain runs a simulation.
Right, you visualize the outcomes.
Yeah, I visualize stepping in it, bad outcome. I visualize trying to walk around it, but I see a cyclist coming, bad outcome. I visualize jumping over it. My internal physics engine calculates my current momentum, the estimated distance, and the required force.
And it predicts a successful jump.
Exactly. And only after running all those simulations do my muscles actually fire to execute the leap.
And the quality of your jump depends entirely on the accuracy of your internal world model. If your model correctly accounted for the slippery mud on the takeoff edge, your shoes stay dry.
But if my model was flawed and missed that detail, I slip and fall.
Precisely. And LLMs cannot do this. They do not simulate physical reality. If you ask an LLM how to cross the puddle, it just strings together words that statistically sound like a plan based on its training data.
Right. It cannot dynamically simulate the physics of your specific body in that specific moment.
Exactly. Now, in a recent podcast interview we reviewed, LeCun gave an incredible analogy for how this simulator should work, using the planet Jupiter.
Oh, I love this analogy. He says, imagine you are an astronomer, and your goal is to predict exactly where Jupiter is going to be in the night sky 100 years from today.
Right.
If you want to make that prediction, you absolutely do not need to model every single swirling gas storm on the surface of the planet.
No, that would be an insane waste to compute.
Exactly. You don't need to know the temperature of every cloud layer or the barometric pressure of the Great Red Spot. To predict the orbit, you literally just need 6 abstract numbers.
3 numbers representing its exact coordinates in space, and 3 numbers representing its velocity and trajectory.
That Jupiter analogy is the perfect distillation of JEPA, which stands for Joint Embedding Predictive Architecture. It explains exactly why previous attempts to build AI world models failed.
Yeah, because before JEPA, researchers tried to build world models using generative AI.
How did that work?
Well, if they fed an AI a video of a car driving down a street and asked it to predict what happens next, the generative model would try to draw the next frame, pixel by pixel.
Oh, so it was trying to model every gas storm on Jupiter.
Exactly the problem. Think about the computational waste. If the camera's looking at a tree blowing in the wind, the generative model wastes enormous compute trying to guess the exact subpixel movement of every single leaf.
But the movement of the leaves is high entropy noise, right?
Yeah.
It is chaotic and largely irrelevant to the core physics of the scene.
Right. The model is so busy drawing the leaves that it fails to predict that a child is about to run into the street.
Because the micro level of the real world is infinitely noisy and unpredictable. You can't render it all. So how does JEPA bypass this?
JEPA bypasses this entirely by not predicting pixels. Instead, JEPA makes its predictions in an abstract representation space.
Abstract representation space. What does that mean in practice?
It takes the visual input and encodes it, compressing it down to only the semantic structural reality of the scene. It ignores the rustling leaves entirely.
So it only extracts the 6 numbers, the abstract concepts of the car, the velocity of the street, and the child.
Exactly. It then predicts how those abstract concepts will interact in the next moment, completely bypassing the need to generate an image.
Okay, I conceptually grasp predicting the abstract meaning rather than the pixels, but how does it actually do that mathematically? The preprints heavily feature something called energy-based models, or EBMs.
Right, EBMs are central to this.
And I feel like energy here isn't talking about electricity or thermodynamics. Can we break down what EBMs are for the listener?
You are correct. It has nothing to do with physical electricity. In machine learning, an energy-based model is essentially a mathematical framework for measuring compatibility.
Compatibility, okay.
Yeah. It defines a scalar function, usually written as E of xy. Think of it as a 3D landscape of hills and valleys.
Okay, I'm picturing it.
The input, let's say a context image, is x. The output, the prediction, is y. If x and y make logical sense together, the model assigns them a low energy score, placing them deep in a valley.
And if they don't?
If they contradict each other, it assigns a high energy score, pushing them up onto a steep hill.
So it's almost like a dating app algorithm for data points.
A dating app algorithm. I haven't heard that one before.
Yeah, think about it. If X is a video of someone releasing a heavy bowling ball, and Y is the sound of a loud crash, they are highly compatible, low energy. They belong together.
Okay, yeah.
But if Y is the sound of a tiny bird chirping, they are completely incompatible, high energy. The model rejects the pairing.
That is actually a great conceptualization. Learning in the JEPA framework is the process of shaping this mathematical landscape.
So the model trains by constantly trying to push correct predictions down into the low energy valleys.
Exactly. And actively pushing incorrect predictions up onto the high energy hills. The system has an encoder that looks at the context and a predictor that tries to guess the abstract representation of what happens next.
So the energy score is just the mathematical distance between what the model predicted and what actually happened in the training data.
Yes, exactly.
But hold on, let me make sure I'm following. If I am looking at the architecture of this, if the model's only overarching goal is to make the predicted representation match the actual representation to get a low energy score, couldn't the AI just cheat?
Cheat? How?
What is stopping the encoder from just being incredibly lazy and turning every single image, every single video into the exact same string of zeros?
Oh,
Right. Then the predictor just guesses 0 every time. The inputs and outputs match perfectly. The energy score is always 0. The model gets a perfect grade on the test, but it has learned absolutely nothing about the world.
you have just intuitively deduced the single greatest flaw in energy-based models. Yeah. In the literature, this is known as the representation collapse problem. It is the absolute bane of self-supervised learning.
Because if the mathematical system can find a degenerate, trivial solution where everything maps to a constant flat line, it will just take it.
Exactly. The system collapses. In the 1990s, early versions of these architectures, known as Siamese networks, suffered terribly from this. The networks would just output the same vector for everything.
It's like a student realizing that if they answer C on every single multiple choice question, they might just pass without reading the book.
Yes. So how does LeCun's JEPA stop the AI from cheating? How does it force the model to actually read the book and learn the complex physics of reality?
Historically, didn't researchers solve this using a brute force method?
They did. It's called contrastive learning. They would explicitly hand-feed the model negative pairs, like an image of a dog paired with the word submarine.
And write a specific mathematical rule forcing the energy score high.
Right. But contrastive methods require massive amounts of data curation and are incredibly computationally expensive. JEPA's brilliance is that it solves the collapse problem without using negative samples at all.
Wow, no negative samples, so how does it do it?
It relies entirely on structural asymmetry and regularization.
Structural asymmetry. Break that down for me. How does making the architecture lopsided prevent cheating?
Let's look at the original IJEPA architecture for images. You have two encoders. One encoder processes the context, which is the visible part of the image.
Okay, and the other one?
The other encoder processes the target, the hidden part the model is trying to predict. Now, the context encoder learns dynamically through standard gradient descent. It is actively trying to figure things out.
Like a normal neural net.
Right. But the target encoder is mathematically restrained. Its weights are not updated directly. Instead, they are updated using an exponential moving average, or EMA, of the context encoder's weights.
Okay, exponential moving average. That basically means the target encoder is lagging behind the context encoder, right? It's a delayed reflection of what the context encoder learned a few steps ago.
Precisely. In the literature, this is often described as a student-teacher dynamic. The context encoder is the student scrambling to make predictions.
And the target encoder is the teacher.
Exactly. Providing the answers based on a slightly older, more stable version of the model's knowledge. Because the student and the teacher are not strictly mathematically identical at any given moment, the system cannot easily synchronize into a collapsed state of all zeros.
Oh, that's clever. The asymmetry breaks the cheat code.
It does. It forces the predictor network to do the hard work of actually bridging the gap between the context and the target.
That is deeply elegant. By mathematically tying one hand behind the system's back, it prevents it from taking the lazy way out.
And this isn't just theoretical philosophy sitting in a white paper on someone's desk. This architecture has evolved rapidly.
Let's move into how this vision is scaling up and actually touching reality then. We have established how JEPA works conceptually predicting abstract representations to build a world model without cheating. Now let's trace the JEPA family tree.
The lineage begins with IJEPA, which stands for the Image-Based Joint Embedding Predictive Architecture. This was the foundational proof of concept.
And the methodology is fascinating. IJEPA takes a single static image. It artificially masks out, meaning it hides several target blocks of the image.
Right.
It then defines a large context block from the parts of the image that are still visible. The AI's task is to predict the abstract semantic representations of those hidden blocks, using only the context block as a clue.
Exactly. So if I give it a picture of a park, and I mask out a dog running on the grass, but I leave the owner holding a taut leash visible in the context block.
The model isn't trying to predict the exact color of the dog's fur or the breed. It is predicting the concept of a heavy object creating tension on the end of that leash.
That is the perfect semantic distinction. And the scale of the masking is crucial here. If the system only masked out a tiny 1-pixel block, the model could easily cheat by just interpolating the colors of the immediately surrounding pixels, just blurring the edges, basically. Right. To force the model to actually learn high-level concepts like gravity, tension, or occlusion. IJEPA masks out massively large blocks, and forces the predictor to look at a spatially distant context block.
It forces the AI to understand the relationships between objects rather than just local textures, and the preprints show this worked brilliantly.
They scaled it up to a massive vision transformer, a VT huge model, ran it across 16 GPUs, and it destroyed downstream benchmarks for things like object counting and depth prediction.
But a static image of a park is easy. The real world doesn't sit still.
Which is exactly why the architecture was immediately evolved into V-JEPA and most recently V-JEPA 2.
Right, the V stands for video.
Exactly. This takes the same latent space prediction objective and applies it to temporal dynamics, meaning it forces the AI to understand how objects change and interact over time.
This is where the numbers in our stack start to look like science fiction. Let's talk about the Epic Kitchens 100 benchmark.
Oh, that's a great example.
So for you listening, Epic Kitchens is a massive data set of point-of-view videos of people doing things in kitchens. Chopping onions, washing pans, opening cupboards. It tests an AI's ability to anticipate actions.
Right. If the AI sees a hand reaching for a knife and a cutting board, what happens next?
And the efficiency of V-JEPA 2 on this benchmark is staggering. We are so conditioned by companies like OpenAI and Google to think that advanced AI requires hundreds of billions of parameters running on server farms the size of football fields.
But V-JEPA 2 is different.
Radically different. V-JEPA 2 has only 1.2 billion parameters. It can run locally on a single consumer-grade GPU.
And that radical efficiency is the direct payoff of operating entirely in the abstract representation space. When an LLM or a generative video model looks at Epic Kitchens, it tries to statistically model the exact pixel location of every drop of water splashing out of the sink.
Which is a huge waste.
V-JEPA 2 doesn't care about the water drops. It only processes the semantic concept. Hand moves pan to water, pan becomes clean. All of its computational horsepower is directed purely at the physics and the logic of the scene.
And that efficiency translates to physical robotics in a way that LLMs simply cannot match. The zero-shot robotics applications blew my mind.
Yeah, they are incredible.
The sources detail how V-JEPA 2 enables a robot arm to perform tasks it has never explicitly been trained to do. The researchers tested it on pick-and-place tasks, like looking at a cluttered table and moving a specific block into a specific bowl.
And what were the results?
The robot achieved a 65 to 80% success rate on objects it had never seen before in its entire existence, and it calculated those physical maneuvers 30 times faster than NVIDIA's Cosmos model.
That is the ultimate validation of a true world model. If the AI has built a robust internal simulator of core physics, it intuitively understands how gravity pulls, how friction stops sliding, how a larger object blocks a smaller one.
So it doesn't need to be trained on a million images of a specific coffee mug to know how to pick it up.
Right. It looked at the novel mug, simulates how its robotic grippers will interact with the mug's center of mass in its abstract representation space, verifies the simulated outcome is successful, and then physically executes the plan.
But the bleeding edge of this research doesn't stop with robotics. We also have preprints in our stack on something called LLM-JEPA, and something that seems totally contradictory, LLM-JEPA.
Let's tackle LLM-JEPA first.
Okay, you mentioned earlier that the original IJEPA avoided representation collapse by using that student-teacher asymmetry, the exponential moving average where the teacher network lags behind. LLM-JEPA essentially throws all of that out the window, doesn't it?
It does. LLM-JEPA, which stands for Latent Euclidean JEPA, represents a fascinating maturation from engineering hacks to pure, elegant mathematics.
So no more student-teacher.
Right. The researchers who authored this paper essentially argued that tools like stop gradients and email teachers are crutches. They work in practice, but they are brittle.
Because they require exhaustive human tuning of hyperparameters to keep the model stable.
Exactly. If you get the tuning slightly wrong, the whole system collapses anyway. LLM-JEPA strips the architecture down to its studs and relies entirely on a distributional regularizer called SIGREG.
SIGREG. Sketched Isotropic Gaussian Regularization. That is a terrifying string of words for anyone who didn't major in advanced statistics. I need you to translate isotropic Gaussian distribution into plain English for me.
I can do that. Let's visualize the AI's abstract representation space as a giant physical room. Every time the AI processes an image, it assigns it a location in that room.
Okay, so an image of a cat goes to one corner, an image of a truck goes to another.
Exactly. If the model suffers from representation collapse, it means all the data points are squished together. Every image gets thrown into the exact same spot in the center of the room, or they form a flat, useless line across the floor.
So the AI can't tell the difference between anything anymore?
Correct. An isotropic Gaussian distribution is the mathematical opposite of that. It means the data points are spread out into a perfectly symmetrical, multidimensional sphere.
They utilize the entire volume of the room evenly, radiating out from the center.
Exactly. And what SIGRAG does is act like a strict bouncer in that room. It constantly surveys the data points. If it notices the points starting to clump together or flattening out, it applies a harsh mathematical penalty to the network.
It's like forcing people on a crowded dance floor to spread out evenly so they utilize all the floor space rather than everyone huddling awkwardly in one corner around the snack table.
That is an excellent visualization. SIGRAG forces the representations to utilize the maximum available dimensional space. And because it relies on pure statistical variance rather than lagging teacher networks, it scales linearly and efficiently.
It prevents collapse through mathematical law rather than engineering tricks. That's amazing.
It really is a breakthrough.
Now, I have to bring up the elephant in the room regarding the final preprint. Yann LeCun has been on a literal crusade against large language models.
Yes, he has.
He calls them an evolutionary dead end. He says they possess the reasoning of a house cat. So why on earth is there a paper in his stack of research titled LLM-JEPA? Isn't that an absolute, undeniable contradiction of his entire philosophy?
It sounds like incredible hypocrisy at first glance, I admit. But when you read the methodology, it is actually a brilliant synthesis of ideas.
How so?
The fatal flaw of LLMs, according to LeCun, isn't that they process language. It is how they learn language. They are trained via input-based reconstruction. They try to predict the literal exact next word.
Okay.
LLM-JEPA is an attempt to transplant the philosophy of JEPA, predicting abstract high-level meaning rather than literal details, into a language architecture.
Wait, how do you predict the abstract meaning of a word without predicting the word itself?
By predicting the embedding. Instead of forcing the model to output the specific sequence of letters, APPLE, you train the model to predict the multidimensional mathematical vector that represents the concept of an apple in the latent space.
Oh, wow.
Yeah. The researchers took this JEPA objective and applied it to pre-training and fine-tuning existing language models, testing it across families like Llama 3, Gemma 2, and Olmo.
And what happens when an LLM stops worrying about literal words and focuses on abstract concepts?
The reasoning capabilities skyrocket. The paper details how LLM-JEPA massively outperforms standard generative training objective on highly complex reasoning benchmarks.
Okay, example.
On the GSM-AK benchmark, which is a brutal gauntlet of multi-step grade school math word problems, and the SPIDER benchmark, which requires the model to read complex text and generate functional SQL database code, the JEPA-trained models were significantly more accurate and robust.
That is a total vindication of the theory. It proves that even when you are trapped in the discrete, tokenized world of language, aiming for abstract meaning yields deeper reasoning than obsessing over the next token.
Exactly.
And this technical triumph perfectly sets the stage for the massive financial realization of all this theory. We have the philosophy, we have the math, we have the benchmark validations. Now we're talking about industrializing the paradigm. Let's look at AMI labs.
Yes, theory and preprints are wonderful for academia, but if you want to truly challenge the entrenched trillion-dollar dominance of companies like OpenAI and Google, you need staggering amounts of capital and real-world commercial deployment.
And that is exactly what dropped on the industry's head in March 2026 with the official launch of Advanced Machine Intelligence Labs, or AMI Labs.
Right.
The numbers surrounding this launch are frankly hard to wrap your head around. The company was founded in January 2026. It officially launched in March. It is headquartered in Paris.
And they actually had President Emmanuel Macron texting congratulations, highlighting this as a major victory for European tech sovereignty.
Which is huge. And out of the gate, they raised a $1.03 billion seed round. I want to emphasize that word to you listening. A seed round.
It's unheard of.
Raising $1 billion to figure out product market fit values the company at $3.5 billion pre-money before they even have a consumer product. This isn't two guys coding in a garage. This is a fully funded, all-out assault on the generative AI landscape.
The cap table, the list of investors, tells you everything you need to know about how seriously the market is taking LeCun's critique. We are seeing participation from Cathay Innovation, Bezos Expeditions, Toyota Ventures, and crucially, NVIDIA.
Wait, NVIDIA invested?
Yes. When the company that makes the chips powering the generative AI boom hedges its bets by investing in a world model startup, it signals a massive industry shift.
You also have Eric Schmidt, the former CEO of Google, writing checks.
Exactly. These major players clearly believe that the current generative paradigm is hitting an asymptotic wall, and latent space world models are the necessary bridge to the future.
And the team they have assembled is ridiculous. The European tech press is calling it a luxurious lineup, which sounds very Parisian.
He does.
You have Alex LeCun serving as the CEO. He is a heavy hitter, the co-founder of the AI medical company Nabla, and a former engineering director at FAIR under LeCun.
But the truly disruptive hire is Saining Ji as Chief Science Officer.
Right.
He was a lead researcher at FAIR, but he is most famous as the architect of diffusion transformers. That is the exact underlying technology that powers OpenAI's Sora, the video generation model that shocked the world.
That feels like stealing the enemy general's best tactician. Why would the guy who essentially perfected generative video jump ship to a company that believes generative AI is a waste of compute?
Because she understands the limitations of his own creation better than anyone. He knows that Sora is a brilliant physics simulator, but it is trapped in pixel space.
Oh, I see.
By bringing Xi on board as Chief Science Officer, AMI Labs is bridging the gap. They're taking someone who deeply understands complex video dynamics and tasking him with translating that into the highly efficient latent space environment of a JEPA world model.
That is a brilliant move. The lineup also includes Pascal Fung as Chief Research and Innovation Officer, an expert in ethical and safe AI deployment, and Laurent Solly, a formidable former Meta VP handling operations as COO.
And LeCun himself is sitting at the top as Executive Chairman.
Though he was very self-deprecating about this in the press, he explicitly stated he took the chairman role because he is too old and disorganized to run the day-to-day operations of a hyper-growth startup.
So his job is to provide the long-term scientific vision and act as the intellectual gravity for the team.
But $1 billion burns fast if you don't have a business plan. They aren't just doing theoretical cognitive science here. They are deploying this technology to impact human lives immediately.
And their first major strategic partner is Nabla, focusing exclusively on the healthcare sector.
The choice of healthcare as the first proving ground is incredibly calculated. It highlights the fundamental life or death difference between LLMs and world models.
Healthcare is the ultimate high-stakes environment. You cannot afford to be mostly right. Large language models, as we've discussed, operate probabilistically. They generate text based on statistical likelihoods. They guess the next word.
And guessing leads to hallucination. When an LLM hallucinates a line of Python code, your web scraper crashes, you read the error log, and you fix it. It's annoying.
Right.
But if an LLM is integrated into a hospital network and it hallucinates a patient's penicillin allergy, or it hallucinates the decimal point on an insulin dosage, someone dies. The stakes are infinite.
Precisely why hospitals have been extremely hesitant to let generative AI anywhere near actual patient care decisions. High-stakes environments require deterministic reasoning. They require auditable safety guardrails.
And JEPA solves this.
Because a JEPA world model performs what-if simulations in an abstract space before executing an action, it can evaluate the consequences of its plan against hard mathematical constraints. It doesn't guess, it simulates, verifies, and acts.
Let's roleplay what this actually looks like on the ground. The sources outline how Nabla will use AMI's world models to move beyond what the industry currently calls ambient documentation.
Right.
Right now, medical AI is basically a highly advanced stenographer. A doctor talks to a patient, the AI listens to the audio, and it generates a neat summary for the electronic health record. That's ambient documentation. But AMI is moving toward agentic AI.
Agentic AI means the system transitions from a passive observer to an autonomous actor. It executes multi-step workflows across the incredibly fragmented legacy infrastructures of modern hospitals.
Okay, let's play this out. Imagine a patient. Let's call her Sarah. Sarah comes in with complex migraines. The doctor decides she needs an urgent MRI and a referral to a neurologist. Under the current system, the doctor tells Sarah the plan, and then a human administrative team spends 3 days fighting with insurance portals, checking the neurologist's schedule, and navigating the hospital's internal imaging department.
That's a mess.
If an LLM tried to do this, it might generate a polite email to the neurologist, but it couldn't reliably navigate the 6 different conflicting legacy software systems required to book the MRI without hallucinating a billing code.
Exactly, but an agentic AI powered by a world model approaches this entirely differently. It receives the goalbook, MRI, and neurologist for Sarah.
And then?
It builds an internal simulation of the hospital's digital infrastructure. It anticipates obstacles, It simulates logging into the insurance portal. It verifies that Sarah's specific HMO requires a prior authorization code for this specific MRI machine.
Oh, wow.
It runs a simulation of scheduling the neurologist and realizes the neurologist is on vacation next week, so it simulates finding the next available specialist within her network.
And it does all of the simulation in milliseconds in the latent space. It maps the entire causal chain of events, verifies that every step aligns with HIPAA compliance and clinical safety guardrails, and only then does it actually click the buttons to execute the workflow.
It is cause and effect physical reasoning applied to hospital administration.
It is a profound leap from text generation to autonomous operational execution. And to be clear, Alex LeCun, the CEO, acknowledges this is a long-term play.
Yeah, he stated to the press that AMI Labs needs at least a solid year of foundational research before launching their first practical, limited application, with full-scale autonomous agentic systems coming a few years after that.
But that foundational difference, the ability to act based on simulated, verifiable reality rather than probabilistic text generation, is what convinced the smartest money in Silicon Valley to part with $1 billion.
Which brings us to the ultimate philosophical endgame of this entire saga. We've seen the breakdown of the old paradigm. We have explored the beautiful math of JEPA. We have witnessed the billion-dollar commercial launch.
But where does Yann LeCun think this is taking the human race? The AMI Labs camp is pushing for a profound, permanent shift in how the entire scientific community defines the ultimate goal of artificial intelligence.
For decades, the Holy Grail, the undeniable North Star of the AI industry, has been artificial general intelligence, or AGI. Every major CEO, from Sam Altman to Demystifying talks about building AGI.
Right.
But in a highly controversial paper published in February 2026 titled AI Must Embrace Specialization via Superhuman Adaptable Intelligence, LeCun and his co-authors effectively declare war on the concept of AGI, dismantling it as an unscientific myth.
They argue that the very definition of AGI is overloaded, contradictory, and essentially useless as a serious engineering benchmark.
The most common pop culture definition of AGI is simply an AI that can do everything a typical human can do. But the authors of this paper ask a deeply cutting biological question. Are humans actually general?
That's a great question.
The paper dives into evolutionary biology to prove that humans are not general intelligences at all. We suffer from an immense illusion of generality simply because we cannot physically perceive our own cognitive blind spots.
Oh, that's interesting.
Human intelligence is, in reality, a highly specialized, incredibly narrow set of cognitive tools that evolved for one specific purpose: biological survival in a physical, terrestrial environment.
We are incredibly miraculously good at reading subtle facial expressions to determine if someone is lying. We are amazing at walking upright on a rocky, uneven mountain trail without falling over. We can throw a rock at a moving target with terrifying precision.
Those are our specializations. But look at what we are biologically terrible at. We cannot navigate or even visualize a 100-dimensional mathematical space.
Definitely not.
We cannot perform high-speed, complex calculus natively in our heads. We cannot instantly parse and correlate patterns across petabytes of tabular data. Our working memory can hold roughly 7 items at a time.
Right. So, the paper argues, if we benchmark artificial intelligence strictly against human capabilities, we are arbitrarily limiting a cosmic technology to our own microscopic evolutionary niche.
Exactly.
I love this argument. It means trying to build AGI by strictly copying human intelligence is like an engineer in the 1800s trying to build the ultimate flying machine by strictly copying the anatomy of a pigeon.
Yes.
You might build a really neat mechanical ornithopter with beautiful wooden wings that flap up and down, but you will never invent the jet engine. You will never break the sound barrier if you artificially limit your engineering to feathers, hollow bones, and muscle tissue. We need to stop trying to build digital humans.
That analogy perfectly captures the paradigm shift. And this is why the paper introduces a new, highly specific North Star for the industry to replace AGI Superhuman Adaptable Intelligence, or SAI.
Let's lay out the formal definition of SAI because it is crucial. The paper defines superhuman adaptable intelligence as a system capable of adapting to exceed human performance at any specific task humans can do, while also being able to adapt to tasks entirely outside the human biological domain that possess utility.
The operative word there is adaptable. The goal of SAI isn't to pre-program a monolithic, trillion-parameter model with every possible skill in the universe simultaneously.
Right.
The goal is to build a highly efficient, latent space system that can rapidly acquire new skills on the fly, whether those skills are familiar human tasks like writing code or completely alien, non-human tasks like navigating quantum chemistry.
And the paper summarizes this philosophy with a fantastic, memorable quote: "The AI that folds our proteins should not be the AI that folds our laundry."
Specialization is the feature, not the bug. The system adapts to the specific problem, but this creates a massive measurement problem. With large language models, evaluating them is easy. We just treat them like high school students and throw standardized tests at them, the bar exam, the SATs, the medical boards. But if SAI is about fluid adaptation to both human and non-human tasks, how do you mathematically measure it?
Oh, I see. That exact problem was solved in the subsequent March 2026 paper by researcher Maitri Anirudhbhai Savalia, who proposed a brand new metric called Adarat, denoted in the literature by the Greek letter rho.
Yes, Adarat. If the SAI framework is the philosophy, Adarat is the formal measurement instrument required to quantify it. It completely shifts the focus from static accuracy to adaptation speed.
The math behind Adarat is fascinating because of what it punishes. It is a dimensionless metric. It measures the performance gain of a model on a new task. It normalizes that gain against the human baseline and the inherent complexity of the specific domain. And then, crucially, it divides all of that by the computational cost required to learn it.
The inclusion of computational cost is what makes Adarat revolutionary. It exposes the brute force inefficiencies of LLMs that standard accuracy metrics completely hide.
The Savalia paper provides a striking, highly practical example from the healthcare domain, right?
It does. Imagine you have two different AI models,
Yeah.
and you are training them to classify early-stage lung cancer from 3D CT scans. After the training period is over, you test them, and both models achieve an identical accuracy rate of 88.9%.
Okay.
Under the old AGI paradigm, these models are tied. They are equally intelligent.
They both got a B+ on the test.
Exactly. But when you apply the Adarat metric, a massive discrepancy appears. Under Adarat, there is a staggering 46% difference between the two models.
Wow. Why?
Because the first model achieved that 88.9% accuracy drastically faster. It required significantly less compute, and it adapted to the complex 3D domain of the CT scan far more efficiently. It demonstrated high adaptability.
And the second model.
The second model, likely an overloaded generative architecture, only achieved that score because it was brute forced. The engineers burned immense amounts of electricity, feeding it millions of images until it effectively memorized the dataset patterns.
That is a total paradigm shift for the business of AI. It completely changes the incentive structure for developers and CEOs.
It really does.
Under Adarat, you are no longer rewarded for just building a bigger data center and burning billions of dollars of electricity to brute force your way to the top of the leaderboard. You are rewarded for elegant, rapid learning. You are rewarded for building a model that intuitively understands the physics of the problem.
And the paper doesn't just propose the metric. It provides direct empirical proof that this kind of hyper-efficient, rapid adaptation is currently possible using latent space architectures.
What's the proof?
It highlights a specific vision model called DynoViv2 VTS. The researchers tested it on the CFAR10 image dataset. CFAR10 is a classic notorious benchmark filled with tiny, complex images of airplanes, cats, and dogs.
Oh yeah, I know that one.
Standard convolutional neural networks struggle with it, requiring tens of thousands of examples to learn the features. DynoV2 achieves superhuman performance on CFAR10 using only 10% of the available training data.
Superhuman performance by looking at only 1/10 of the flashcards.
Yes, that is the true essence of superhuman adaptable intelligence. It isn't about knowing everything at once. It is about learning a new domain faster and with exponentially less data than a human ever could, driven by the structural intuition of a robust internal world model.
Oh, take a breath. We have covered an absolute mountain of ground today, and the implications are staggering.
We really have.
We started with the very real, visceral corporate drama of Yann LeCun's bold departure from Meta. We explored his deep frustration with an LLM-pilled culture that was so desperate to maintain the illusion of progress that it was fudging the benchmarks of Llama 4.
And we unpacked his foundational Moravec-inspired critique that stringing together the most probable next word is absolutely not the same thing as possessing a grounded understanding of physical reality.
We then dove deep into the elegant mathematical antidote JEPA and world models. We explored how predicting abstract representations using energy-based models completely avoids the computational waste of pixel generation.
We saw how structural asymmetry in IJEPA And later, the pure statistical elegance of SIGREG and LeJEPA prevents the models from cheating and collapsing.
We tracked the evolution of this architecture as it scaled up to V-JEPA 2, watching it enable robotic arms to perform zero-shot physical manipulation on objects they had never seen before.
We saw how LLM-JEPA is unexpectedly bringing that same embedding space efficiency back into the realm of language, boosting reasoning on complex math and coding tasks.
We witnessed the billion-dollar birth of AMI labs and role-played how their world models are shifting healthcare from passive documentation to deterministic, agentic AI execution.
And finally, we explored the profound philosophical shift away from the anthropocentric, unscientific myth of AGI, moving toward the measurable, rapid learning of superhuman adaptable intelligence, quantified by the new Adderite metric.
So, to you listening, when you are prepping for your next big tech strategy meeting or you're scrolling through the latest breathless headlines about a new chatbot that can write a decent screenplay, I want you to remember the core lesson of this deep dive.
It's an important one.
Remember that a highly detailed map, no matter how vast or beautifully drawn, is profoundly different from possessing an internal, dynamic simulator of how the universe actually functions. Predicting the next word is not understanding.
I want to leave you with a final thought to mull over, building on the concept of superhuman adaptable intelligence.
Okay, let's hear it.
We have spent the last 70 years desperately trying to build artificial machines in our own biological image. We constantly measure their intelligence by how well they mimic human speech, human logic, and human flaws.
Right.
But if SAI shifts the focus entirely away from human mimicry and purely toward the speed of adaptation, the sheer velocity of learning and multidimensional latent space, it raises a profound question. Are we about to enter an era where AI doesn't just learn faster than us, but inevitably invents entirely new, completely alien ways of understanding the physics of the universe? Ways that we, trapped in our evolutionary biology, literally lack the sensory hardware to comprehend.
Now that is a thought that will keep you up at night. Thank you so much for taking this custom, expansive, deep dive with us today. It has been an absolute privilege exploring the bleeding edge of world models and Yann LeCun's billion-dollar vision with you. Stay incredibly curious, keep questioning the consensus, and we will see you on the next deep dive.